All right, so we made it through method of joints, and as you've seen, it takes a fairly long time to go through and find all the different member forces, all the internal forces and all the members. Today we'll see a second way to do that called the method of sections. It's slightly faster. It's definitely better in certain cases, which I'll get to. So method of sections, just like method of joints assumes that if the entire structure is in equilibrium, then each individual joint is in equilibrium, and you can look at each individual joint. Method of sections, kind of the same principle, except instead of looking at individual joints, I'm looking at a whole portion of the truss. So what we basically do is we pass an imaginary section cut. So essentially we pretend we cut this thing in half, and I use the term half lightly there. It's not necessarily exactly in half. You can cut it wherever you want, but the point is you cut it, and then you only look at one part of it. So you essentially throw away the other part or other half. And so again, if the whole thing's in equilibrium, then each of these two parts is in equilibrium. And so only have to look at one. And what you basically do, just like we did for the method of joints, is each joint or each member coming into that joint was replaced by a force. Same thing here. When I cut through my truss structure, I cut through certain members. Each one I cut through, and only the ones I cut through get replaced by individual internal forces. And so because of that, I'm dealing with this entire portion. I'm dealing with more than a point. So again, method of joints, I only had two equations of equilibrium because I was dealing with a point at a time. Each joint was a single point, so there was no rotation. Here I'm dealing with an entire part of the structure. So rotation is important, which means I can use that third equation of equilibrium, the moments. And so I'm going to have three equations of equilibrium in 2 dimensions. And so I can solve for up to 3 unknowns, meaning that each of my section cuts, when I cut through the truss, I want to make sure I cut through no more than 3 members, because those members will be replaced by unknown forces. And if I have more than 3 of them, I can't solve for them. So that is the method of sections. Biggest advantage to this is if I only care about a certain part of the truss. So a lot of times I can look at a truss and see where the biggest external forces are, and where the biggest external forces are generally corresponds to where the biggest internal forces are. So if that's kind of the part of the truss that I'm worried about breaking, I can just pass my section cut through that portion and then solve for those unknowns. And since those are the only ones I care about, I don't have to go through the entire method of joints, going through the entire structure to find the 3 that I care about. So this is where this is really helpful. This is when you only need a certain number of member forces and they're all kind of together. So general procedure, similar to method of joints again, I want to construct the free body diagram for the entire truss structure. I can solve for those support reactions. I may or may not need them, just like we saw in method of joints. And then next step is pass a section cut through the truss and cutting no more than 3 unknown members. And those 3 members get replaced by internal reaction forces. And then basically throw away 1/2 of that truss structure and use the rigid body equilibrium, what we did on day 9 and 10, to find the unknown member forces, all 3 of them, using the 3 equations of equilibrium. So generally force in x direction, force in y direction, and some moment around some point. Although, as we're going to see later today in class, when we do examples of this, sometimes easier to use 3 moment equations. So moments around different points, because those will generally give you just one member force in each individual equation. You don't have to deal with 3 unknowns for 3 equations. You can generally find just one unknown using the appropriate point. Again, we'll see that later today in class. So just like method of joints, the description of this is slightly vague. It sometimes helps to see examples. So that's what we will do later today in class.